Today I'm excited to show you our MWAVE Neural Network architecture. It's a cutting-edge model inspired by quantum fractal patterns. So this visualization demonstrates how our model processes complex quantum data structures through multiple layers of very specialized attention mechanisms. So let's start with the architecture overview at the top screen. So our model implements a multi-layer transformer with some very unique properties. In the first card, you'll see our model structure uses 128 dimensional beddings across 6 transformer layers. We're leveraging 16 attention heads per layer to process data from a massive 10,000 node quantum lattice. The middle card shows our quantum parameters. The most important is our harmonic Q frequency, which is over 8 quadrillion hertz, which drives our temporal superposition across 10 time frames. So the beta S parameter is particularly interesting as it controls our fractal scaling structure. And finally, our training configuration uses a batch size of 32 with a conservative learning rate of 0.0005 for numerical stability when dealing with these complex quantum structures. Now let's look at the network diagram. This is for the architecture. Each of these purple blocks represents one of our 6 cognospheric layers. I can click on any layer and see its components. Each layer contains 3 main components: MWAVE Attention, Temporal Superposition, and feed-forward network for neural fractal processing. So the MWAVE Attention has fractal scaling, the temporal superposition has multi-frame quantum prediction, and the feed-forward is for neural fractal processing. All of these work together to create an entangled representation of the quantum data flowing through the network. So the data visualization. So the chart at the bottom shows how our model transforms input data. The blue line represents the input data, and the purple line shows how the model processes the data. Let me demonstrate how adjusting the beta fractal coefficient affects the output. So I'll increase the beta value using the slider. And you can see how the model's output changes. The higher beta value amplifies the fractal patterns in the data, while the lower value maintains a more conservative transformation. So that parameter is actually pretty crucial for tuning the model's sensitivity to quantum coherence patterns. For those interested in the implementation details, I can click Show Details. And here's my model architecture down here as well too. You can see the exact structure of the UKE transformer, including the embedding layer that projects our 10,000 node input to the 128 dimensional working space. So our 6 cognospheric blocks with their components and the output projection go back to the original dimensionality. So the visualization helps us understand how the MWAVE architecture processes quantum data through its specialized layers. The interactive elements let us explore how parameters like the fractal coefficient affect the model's behavior. Our early experiments show promising results for modeling complex quantum phenomena, with coherence matrix improving significantly through training. We're continuing to refine these models for applications in quantum computing, material science, and especially energy systems. I'm happy to answer any questions about the model or this visualization. Thanks for your time.